Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 4 on inverses of linear functions. Now we discussed inverse functions back in Unit 1 and we want to kind of continue to work with inverses throughout this course but with a variety of different function types. Now of course this unit is all about linear functions, so let's jump in and talk about their inverses. Now, as we've seen, all one-to-one functions have inverses that are also functions. Remember, one-to-one functions are functions that, for different inputs, you always get different outputs. Most linear functions are one-to-one and thus have inverses that are also functions. So, let's get into exercise number 1. On the grid below, the linear function y equals 2x minus 4 is graphed, along with the line y equals x. How can you quickly tell that y equals 2x minus 4 is a one-to-one function? All right, try to see if you can remember what our test was, our graphical test for one-to-one functions. Pause the video now. All right, well, it passes the horizontal line test. All right, we'll remind ourselves what that is in a second. It passes the horizontal, line test. Getting like weird symbols. Now remember, the horizontal line test is this idea that if we have the graph of a function, and keep in mind, we're talking about this blue line right here, y equals 2x minus 4. The idea is if we take any horizontal line, and I'm going to just kind of quickly sketch these in, right? Any horizontal line that we graph and it intersects the graph at most once, then it is a one-to-one function. And that's because horizontal lines are constant y values, all right? So if a constant y value hits a graph more than once, that means that an output has been repeated and then the function is not one-to-one. But this one, right, keeps hitting these graphs. The graph of y equals 2x minus 4 only once, and eventually I'll explain why y equals x is even there. But for now, I just wanted to review the horizontal line test. All right, let's take a look at letter B. Graph the inverse of y equals 2x minus 4 on the same grid. Recall that this is easily done by switching the x and y coordinates of the original line. Create a table of values below for the inverse. All right. So remember, inverses literally just take inputs and outputs and reverse them, all right? So we have this point here, which is at 0, negative 5. Let me just sort of write that down. 0, negative 5. Oh, nope, that's not 0, negative 5. That's 0, negative 4. All right, that means that the inverse must contain the point negative 4, 0. All right. Likewise, here we've got the point 1, negative 2, which means the inverse must contain the point negative 2, 1. So what I'd like you to do is continue doing that. Continue grabbing points off of the line y equals 2x minus 4. Don't worry about the line y equals x for right now. And if you need to, maybe keep writing them down and then flipping those x and the y coordinates to generate a table of values that will allow you to then graph the inverse. Pause the video now and go ahead and do that. All right, well here we have the point 2, 0. So when we flip those around, we'll have the point 0, 2, right? Here we've got the point 3, 2, I think that's 3, yeah, 3, 2. So when we flip those, we'll have 2, 3. Here we've got the point 4, 4. Of course, when we flip those, we'll just have 4, 4. Here we have the point 5, 6. When we flip those, we'll have the point 6, 5. And finally, way up here, well, actually, that's it. No. We have the point 6, 8. When we flip that, we have 8, 6. All right, that will allow us now to plot the graph of the inverse. Let me just erase these really quick. Maybe I'll go in red so that we can have a really nice difference. So I've got negative 4, 0. I've got negative 2, 1. 0, comma 2, 2, comma 3, 4, comma 4, 6, comma 5, and 8, 6. All right, and there's our inverse. Okay, real simple. Plotting inverses, take all of the points, or some points, not all the points, but some points on the original function, switch the x and y coordinates, plot, and see what you have. Okay, let me go back to blue real quick. Now we can finally bring y equals x in. Let's take a look at letter C. What can be said about the graphs of y equals 2x minus 4 and its inverse with respect to the line y equals x? So how do these two lines relate to one another compared to the line y equals x? Pause the video now and see what you can put down. Well, they're symmetric across y equals x. They are symmetric across y equals x. Right? In other words, if I took this point and I reflected it over y equals x, it would hit that point. Same thing here, right? Each one of these points is just the reflection of the other one across y equals x. Now, if you remember from geometry, that should make sense, because in geometry, when you wanted to reflect a point across the line y equals x, and this was probably something that you had to just memorize back in that course, you simply switched the x and the y coordinates. So given that that's how we graph an inverse function, it would make sense always that a function and its inverse are symmetric across the line y equals x. All right, let's take a look at letter D. Using the graph, write the equation of the inverse in y equals mx plus b form. All right, that should be easy enough. Forget about inverses or anything else. Simply take that line. You should be able to identify its y-intercept and its slope. Write down its equation. Take a moment to do that. All right, well, we can see, and let me go back in red just so that we keep in mind which one's which. Very easy to see what the y-intercept is, right? The y-intercept is 2. Slope is a little bit trickier, but we have 2 units of run versus 1 unit of rise. So its slope is 1/2. So that means the equation of our inverse is y equals 1/2 x plus 2. You might think that, if you had two lines or two linear functions that were inverses, if one slope was positive, the other slope would be negative. But that is definitely not the case, right? This one has a slope of 2, this one has a slope of 1/2. All right? And certainly the x-intercept of this line became the y-intercept of that line, but that's a little bit trickier to kind of process. But it's easy enough, 1/2 x plus 2. Now, we would like to be able to come up with the equation of an inverse without having to graph it and then look at the graph and deduce or figure out what the equation of the inverse is from the graph. So let's take a look at the method for finding inverses in letter E. Find the equation of the inverse by switching x and y in the original equation and then solving for y. Why does it make sense that this method works to find the equation of the inverse function? All right, great. So I'm basically telling you what the method is, but let's go through it and ensure that we come up with this equation again. So the method for finding inverses will always be the same, equations of inverses. We're going to take the equation of the original function and we're simply going to switch the role of input and output. So this is my original, right? To find the inverse, what I'm going to do is I'm going to switch x and y. And we can already start talking about why this makes sense. One reason why it makes sense is simply because the inverse literally switches the roles of inputs and outputs. So, I mean, there's no better way of switching the roles of inputs and outputs than basically taking the input and renaming it the output, or sorry, taking the output, renaming it the input, and taking the input and renaming it the output. But let's actually go through this now and solve for y and show that we get this, right? It's easy enough. I just need to add 4 to both sides. All right, that's going to be giving me x plus 4 is equal to 2y. Now I'll divide both sides by 2. I'll get y equals x plus 4 divided by 2. But now if I distribute that division, I'll get x divided by 2 plus 4 divided by 2. And that will give me y equals 1/2 x plus 2. Now, why does it make sense that this method will work? Well, it makes sense because once x and y are switched, whoops, that was nice. Once x and y are switched, you need to use inverse operations to solve for y, right? So literally, right, this particular function multiplies the input by 2 and subtracts 4. Once we switch them, right, in order to get the output back, we literally have to do the opposite of what the original function did and in the opposite order in order to solve for the output. So we are literally forced then by this algebraic procedure to do the inverse of what the original function did and in the opposite order, thus giving us the inverse function. And this is one of the key points about all inverses, finding the equation of an inverse. Let's take a look. Algebraic method for finding the equation of the inverse function. If y equals f of x is a one-to-one function, then the equation of its inverse function can be found by switching the input and output variables, x and y, and then solving for the output variable, the y variable. We're going to be doing this process, a number of times in this course. I mean, it's not going to come up every period or anything like that, but there's going to be a number of times when we're working with a particular type of function, and we want to find its inverse function because we know the original one's one-to-one. So it will always be a two-step procedure. Take the original equation, switch x and y, and then solve for y. Let's take a look at exercise number 2 to get some practice on this. Which of the following represents the equation of the inverse of y equals 5x minus 20? Well, we did just do one of these, so what I'd like you to do is try to figure it out for yourself. Switch the x and the y, and then solve the equation for y, and see which one of these is correct. Pause the video now and see what you get. All right, let's do it. So step 1, right? We are going to make this into x equals 5y minus 20. All right, now we want to solve for y. So I will add 20 to both sides. I'm going to flip-flop the equation really quick. I'll divide both sides by 5. Real critical to make sure you distribute that division. So that's x divided by 5 plus 20 divided by 5. And that's going to be y equals 1/5 x plus 4. And there it is. By the way, notice in our last example, our original linear function had a slope of 2, and its inverse had a slope of 1/2. In this particular problem, our original linear function has a slope of 5, and its inverse has a slope of 1/5. And that will always be the case for the inverse relationship between two linear functions, linear, right? Which is that whatever the slope of the one is, the slope of the inverse is the reciprocal of it, the flip of it, if you will. Now, it's a little bit different than two lines that are perpendicular to each other, where the slopes are negative reciprocals. Here, if the original function has a positive slope, its inverse will also have a positive slope. And likewise, if it had a negative slope, which we haven't seen yet, its inverse would also have a negative slope. All right, let's keep working with these. Now, although this is a simple enough algebraic procedure, certain problems can lead to common errors when solving for y. Care should be taken with each algebraic step. Let's take a look at exercise number 3. Which of the following represents the inverse of the linear function y equals 2/3 x plus 8? Okay, well, of course, what's going to make both this problem and our next exercise difficult is the fact that fractions get involved. What I'd like you to do is pause the video and see if you can figure out the equation of the inverse for this particular linear function. Okay, two-step procedure. Step 1, let's switch x and y. Step 2, let's solve for y. Now, so far, this doesn't seem really any different than the one that we just did. I'm going to rewrite this as 2/3 y equals x minus 8. But of course, one of the big differences is we don't really want to divide both sides by 2/3. That's ugly. It's a pain. You don't want to do that. What's better is multiplying both sides by 3/2. Now, one of the keys, though, is that we have to multiply everything on the right side by 3/2. It would be so tempting to just multiply the x by 3/2, in which case you'd get choice 1, y equals 3/2 x minus 8. And that would be incorrect, right? Because what we have to do is distribute that 3/2 through the parentheses. Now 3/2 times x is just 3/2, but 3/2 times 8, well, that is equal to 12. Now in this case it's negative 12 because there's a subtraction there, but there is our inverse. And I've seen it time and time again. Somebody will do a problem like this. They know they have to multiply both sides by 3/2, but they'll only apply that 3/2 multiplication to the x and not to that y-intercept. And therefore, they'll get the wrong answer. And that wrong answer will be there because the test makers also know that people are liable to do that. Let's take a look at number 4. What is the y-intercept of the inverse of y equals 3/2 x minus 9? All right, very, very similar problem. Why don't you pause the video now and try to figure it out? Well, probably the best way to do this is do exactly what we did in the last problem and then just pick off the y-intercept. So here we go. I've got x is equal to 3/5 y minus 9. Add 9 to both sides. I'll get x plus 9 is equal to 3/5 times y. Multiply both sides by 5/3. Again, got to watch out because that 9 needs to be multiplied by the 5/3 as well. So when I distribute that 5/3 into the parentheses, right, I'll have 5/3 times 9. Do a little bit of cross cancellation. 5 times 3 is 15. So the equation of my inverse will be 5/3 x plus 15, which means, of course, the y-intercept is just 15. All right, simple as that. Let's keep taking a look. All right, now, working in point-slope form. Sometimes we will work with linear functions in their point-slope form. The method of finding the inverse does not change because the linear equation is written in a different form. It just doesn't, right? Still switch x and y, solve for y kind of thing. So exercise number 5. Which of the following would be an equation for the inverse of y plus 6 equals 4 times x minus 2? Well, pause the video now and see if you can figure out the equation of the inverse. This one's actually relatively simple, right? If I switch my x and y, I'll get x plus 6 is equal to 4 times y minus 2. Now, I could definitely distribute the 4 through the parentheses. I could do that, except all of these are written in point-slope form just as this is written in point-slope form. So what I'm going to do is I'm actually going to multiply both sides of this equation by 1/4. And that's going to give me y minus 2 is equal to 1/4 times x plus 6. And that is right here. Y minus 2 is equal to 1/4 times x plus 6. Now, if you'd been paying attention earlier when I said, look, the slope of the inverse will always be the reciprocal of the slope of the original function, then you probably could have picked this one out right away. The slope of this function is 4. The slope of its inverse would have to be 1/4, and that is the only one with a slope of 1/4. Now let's take a look at number 6. Which of the following points lies on the graph of the inverse of y minus 8 equals 5 times x plus 2? Explain your choice. All right, well, pause the video now and see if you can figure it out. Now, I'm sure that there are easier and harder ways to do this, but this doesn't have anything to do with switching x and y and solving for y. Don't get me wrong, you could do that. You could definitely switch x and y, solve for y, and then, I don't know, substitute every one of these points in to see which one made the equation true. But this is the easier way of doing it. When I look at this function, what I can say immediately is on the original line, we know that the point -2, 8 must lie on that line, right? Just based on what we know about the point slope form of a line, it must go through the point -2, 8. But that then means that the inverse line, must then contain the point 8, -2, because that's what inverses do, right? They take the x and y and they reverse them. And therefore, it is simple to find that. Now, in terms of explaining your choice, this is the explanation. The original line contains the point -2, 8, which means that the inverse must contain the point 8, -2. All right, let's take a look at one last problem. Exercise number 7. Which of the following linear functions would not have an inverse that is also a function? Explain how you made your choice. Ooh, this is kind of interesting. So there is one type of linear function, one type, that will not have an inverse that is also a function. And one of these is that type. Pause the video now and see if you can figure it out. Well, one thing you could do is literally switch x and y in every one of these things and see if something occurs to you. But look, ultimately speaking, right, the correct answer is going to be y equals 2, right? And the reason it's going to be y equals 2 is this is a horizontal line. Its inverse will be x equals 2, which is a vertical line, which is not a function. So even though horizontal lines are not interesting linear functions, because they are just literally a constant value, y equals 2, they are still a function, okay? And all functions have inverses. Now, whether those inverses are also functions themselves all depend on whether they are one-to-one functions or not. Y equals 2 is most certainly not a one-to-one function because it has multiple repeated y values. In fact, it only has one y value, y equals 2. But what's really cool is you can almost think about it as, hey, look, if I switched y and x here, I'd get x equals y, which, believe it or not, means y equals x and its inverse are the same function, which is cool, but we're going to leave that there. Here, 2y equals x, we'd have 2x equals y. That's still a perfectly good linear function. And down here, we'd have x equals 5y minus 1, which we could rearrange into a perfectly reasonable linear function as well. But this thing, if I switch x and y, y equals 2 becomes x equals 2, which is a vertical line, and vertical lines are most certainly not functions. All right, let's wrap this up. So we're going to be working a lot with inverses throughout this course. They're going to be one of the sort of like big ideas in Algebra 2. And a critical notion when we work with inverse functions is how do we come up with their equations, right? How do we think about their graphs? One thing that we learned about graphs of functions and their inverses is that they're symmetric across the line y equals x. And the other thing that we learned, the bigger takeaway from today's lesson, is how to find the equation of an inverse function. And to do that, we simply take the original function, we swap x and y, and then we solve for the y variable. We do this because in solving for the y variable, we literally have to do all the inverse operations that the original function did in the opposite order, therefore giving us the inverse function. All right, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.